Welcome back. This is the last lecture in the introduction. So this is the end of introduction. So in this lecture, we will look at what we mean by radioactive kinetics and some introduction to artificial elements. Okay, so that there is a pattern in radioactivity is not at all obvious, right? There's a discernible pattern, is not an obvious fact, but there is a pattern, right? So when you look at radioactive decay, so this was first proposed by Rutherford and Soddy in 1902. So the rate of radioactive decay is proportional to uh, the number of atoms that is present. Okay, so that is an interesting feature, which seems to suggest that the radioactive decay of a bunch of particles is not affected by something outside of it, okay, or between interparticle interactions, right? So more or less, the element is decaying independently of each other, right? If it had been, let's say, two particle interaction, it would have been n squared, or if there is a three particle interaction, this term would have been n cubed and so on, right? So that doesn't seem to be the case. It is independent of each other. So a certain fraction of atoms seem to be radioactive, uh, seems to display radioactive decay. But you have to understand that each nucleus seems to be alike, right? So why is that some nucleus are decaying and something else is not decaying? Okay, these are the kinds of questions which we would like to answer. We will look at it, right? If you We'll look at it in some later lecture. So this is just an uh, phenomenological uh, and mathematical description of what is happening. And if you solve this differential equation, you get this kind of a solution. So this is the number of um, radioactive nucleus at t equal to 0, and this is at some time t. So why is this kind of a law important? This kind of a law is important because a kinetic law is suggesting something deeper into the mechanism. Perhaps many of us are familiar with kinetic laws that were first introduced in high school chemistry, right? So if you look at um, this kind of a law is in chemistry called unimolecular kinetics, right? So where each of the molecules seems to be reacting independently of one another. And in chemical kinetics, this can be understood using the concept of temperature, right? Temperature is an average um, measure of average energy, and some of the molecules have greater energy, some have lesser energy, and so on. So there is a way to rationalize unimolecular kinetics in the context of chemical reactions. But nuclear reactions also seems to show unimolecular kinetics. So what is the underlying mechanism is not clear right now. And this notion of temperature is well defined, let's say, or much more relatable in the context of molecules. But how do we think about, let's say, concept of temperature in the context of nucleus? That's not very clear. So what I'm trying to convey is that when you have a phenomenological kinetic law, rate law, that has implications to mechanism, which is what we want to understand. Mechanism is which is what we want to understand, but to document an experimental behavior, you first get a phenomenological kinetic law. So this was done in early stages. It is clear, and in the other part of the class, we are also looking at so-called condensed matter nuclear reaction. One thing which we want to really understand are the kinetic laws for nuclear activity in condensed matter. Um, are they simple? Do they take a simple form like what was shown in the last previous slide? That's not very clear. So we will take up this question in the later part of the class. Sometimes the products of radioactive decay are also radioactive, sometimes more radioactive. So the radioactivity may also increase, right? If the products of the decay is more radioactive, then the overall radioactivity will tend to increase and they may reach a maximum, or for a period of time, they may be approximately constant also. These are all different kinds of behavior depending on the system you're looking at. Um, Again, you can relate this to chemical kinetics, right? There are variety of kinetic equations that is possible, right? If you have a free radical, for example, the behavior is very different. The behavior in liquid, solid, gas phase is very different. Likewise, you may have a variety of radioactive decay law. All these are suggesting more complicated mechanisms. Um, so this is an example of artificial radioactive element generation, right? So when you have an alpha particle is useful for two reasons, right? First, there are natural elements which give rise to alpha particles, so they're readily available. And if you have a charged particle, they can be accelerated in an electric field. Therefore, there are ways of increasing the energy of an alpha particle. In addition, alpha particle is a massive particle, right? It's not like electrons. So the massiveness uh, helps in breaking up the nucleus. For example, when an alpha particle bombards nitrogen atom, you get uh, oxygen and uh, hydrogen, right? So again, 7 plus 2 is equal to 8 plus 1. That is, the atomic number is balanced. 14 plus 4 is equal to 17 plus 1. The atomic weight is balanced. Okay, so this is another simple rule uh, for a radioactive, a nuclear reaction. So this is an important aspect because for a long time, that one atom cannot be changed. This is called transmutation, right? Mutation means change. Here we have nuclear transmutation. Nitrogen is converted to oxygen, right? So for a long time, uh, it was not it was thought that it's not possible to change one atom to another, right? For a long, even Newton, Isaac Newton, worked a lot on uh, transmuting to gold, right? Gold was more valuable. So by some means, if you can get more gold, that was a big deal in those times, even in the modern times, for example. So that it is possible to change the essential nature of atoms is a big deal. So that was done via these kinds of processes, where an alpha particle bombards a nitrogen atom and gives rise to oxygen and proton. So this is another example wherein boron is converted to nitrogen. So there are many more examples. So here you emanate a neutral particle, neutron, and so on. Here, the product itself is naturally radioactive. So phosphorus breaks down to silicon and positron, right? So there are a variety of examples. We will look at these things as we progress in uh, the course. So these are very important thorium-based reactions are very important, especially for nuclear work in India. So we have more thorium. So a lot of work has gone into this kind of reactions in India. So there are, um, uh, for example, this a nuclear decay process, the main thing to notice is that you may have a variety of emanations that eventually uh, the trajectory stops when you reach a stable nuclear bismuth. So this, in a way, completes the introduction. We will look at nomenclature that is utilized for describing a variety of nucleus. These nomenclature is just uh, not for just classifying mindlessly. This is going to tell us some indication of give us indication of nuclear stability. That's why we want to be classifying the nucleus in a variety of ways. We will look at that in the next lecture. Thank you.